This is Lesson 3 of Unit 8, Accumulation Functions in Applied Context. This lesson is going to cover accumulation functions with different situations that we haven't covered already, especially objects in motion. We see a lot of those, but we can be aware that there's a lot of situations where there's some sort of accumulation over time of some sort of product or a distance or something, although we're going to stay away from the distance ones. So this whole section is a series of examples that are related to accumulation functions. So let's just get right into it. So example 1, you received a 10-week-old Basset Hound puppy for your birthday and discovered that he is gaining weight at a rate of e to the 0.0125 t pounds per week, where t is the puppy's age in weeks. At 10 weeks, the puppy initially weighed 14 pounds. What is the expected weight of your new puppy at the end of week 15? So we're going to use the same method that we used before in previous sections. We are going to add to our initial condition, the 14 pounds, the accumulation from where we're starting till the end of the 15th week. So we're starting at week 10. That one didn't show up. So we're starting at week 10 to the 15th week of our growth function for our puppy, which is 0.00125 t dt. So we're going to integrate this and evaluate it over that time interval, and then we'll have the expected weight of our puppy at the end of the 15th week. So we have 14 plus e to the 0.0125 t over 0.0125 t evaluated between 10 and 15 weeks. So when we do that, I just put that in my calculator, and I got that the puppy is going to weigh 19,846 pounds at the end of week 15. Okay. Next example. An electric monorail transport is slowing down at a rate of 2t plus 25 feet per second per second. So you want to make note of the fact that that is the acceleration, where t is the time in seconds. By how many feet per second does the monorail slow down between t equals 1 and t equals 5? Now what we want to find, since this is in feet per second, is we want to find the velocity. So we are going to integrate our acceleration function between the time periods we're asking for, from 1 to 5 seconds. So we're going to have the integral from 1 to 5 of 2t plus 25 dt. And when we integrate that, we get t squared plus 25t. And we're going to evaluate that between 1 second and 5 seconds. So when we do that, it's pretty simple to do. We're going to get 25 plus 25 minus, put 1 in, you get 1 plus 25. So when you do that, you have that should be 125. When you take 5 times 25, you get 125. So that's 150 minus 26. So you get 124 feet per second. Okay, example 3. The number of liters of oil in a tank is changing at a rate of R of t is equal to 0.26 t liters per minute, where the t is the time in minutes. Initially, the tank contained 14 liters of oil. Write an expression that can be used to find the amount of oil in the tank after 10 minutes. Okay, so again, we're given an initial condition of 14 liters that are already in the tank, and we're given a rate at which it's filling. So we want to find after 10 minutes. So we're starting from time 0 to 10 minutes of our function. 0.26 t dt. So when we integrate that, we get 14 plus 0.112. I'm sorry, I can't divide today. 0.13 t squared, and we're integrating that between 0 and 10. So we just have to substitute 10 in, So we get 14 plus multiplying 10 into our function, we get 10 squared, so this will just be 13. So we get 27 liters of oil are in the tank after 10 minutes. Okay, whoops, next example. In number 4, we're to describe the meaning of each expression in context to the given scenario. So the first one says, a function w of t gives the number of water bottles produced by a manufacturer by time t in hours on any given day. Explain the meaning of the expression. So we have an integral going from 4 to 8 of w prime of t dt. So this is going to be the number of water bottles, because when we integrate that, we will get w of t back, which is the number of water bottles. So this is the number of water bottles produced during the 4th through the 8th hour. That's supposed to be a U, not a W. Okay, next part. The amount of oil being drained from your pickup truck is decreasing at a rate of R of t quarts per minute, where t is the time in minutes. What does the expression below mean? So you always want to go back and look at what your functions mean. So R of t means it's the rate of quarts per minute. So we're integrating rate. That will give us the amount. So, and this time we have a value. So what we're going to say is that, and because it's negative, we're draining it. So we're going to say that 0.5 quarts of oil have drained from the pickup from the 3rd to the 4th minute. Or you could say during the 4th minute or the 3rd minute, however you want to word that. I wasn't sure if is it the 3rd minute? What you got? I guess it's the 4th minute, so I just put from the 3rd to the 4th minute. Okay, part C says, Kevin got a gift of $500 from his grandparents for graduation. He deposited the gift into his college savings account. Kevin's savings grows each month at a rate of R of t hundreds of dollars each month, where t is the month of the year. What does the expression below mean? So as you can see, they have taken into account the $500, and because this is 500, you want to realize that the 24 is actually 2,400 that he initially got, and then we're integrating from month 1 to month 12 our rate of growth. So what we're going to say is, by the end of 1 year, or 12 months, however you want to say it, Kevin's savings is $2,400, because that'll be the total amount since we included the starting value. Okay, sometimes, as you guys are well aware, that the AP test likes to give tables. So here's an example using a table. A city bus is accelerating from 0 to 18 seconds. The data for the acceleration, A of t, is recorded in the table below. If the acceleration at t equals 0 is 6 feet per second, find the approximate velocity at t equals 18 using the trapezoidal rule, or trapezoidal sum. Okay, so we are just going to write this out. So I'm going to organize this, because I know that I initially have 6 feet per second here. And then I'm going to add to that all the trapezoidal sums that I get out of the table. And just to recall, just to make this a little easier, you can see that we have even spacing here, that these are all 3 seconds apart. And so every one of them is going to have 1/2 times 3. And then we're going to have 1 plus 4 for the first one. And then we're going to have 4 plus 6. And then we're going to have 6 plus 8. And then 8 plus 7. And then 7 plus 9. And then 9 plus 10. And when I go to simplify this, and I'm assuming that I don't have a calculator, I'm going to group them together. So I'm going to have 3 halves times. Factor that out. I have 1 1, and then I have 2 4s. I have 2 of everything else except the last number. And of course, you can just, if you want, just go ahead and brute force through that. And so when you do that, it just made it easier for organize it in my brain. I'm going to have 6 plus 3 halves times 79. So this is 12 over 2. Plus 237 over 2, so that gives me 249 over 2, which is equal to 124.5 feet per second. Okay, and the other way we see these problems is, of course, our old friend, the graph. The graph at right shows the rate in gallons per hour at which the storm water is being pumped from an overflowing canal. Find the approximate number of gallons pumped from the canal in a 24-hour period. So what we're figuring out here is we're going to find the area under that curve. So we're looking for, that didn't come out right away, so it came out weird. Gallons are gallons of water or storm water. And that's going to equal the integral from 0 to 24 of r of t dt, because I got that because it's telling me that y is r of t. So I am just going to do the same thing, and I'm going to use trapezoids here. This curve is perfect for trapezoids, and they all have a width here of 4, the way the graph is divided. Thank you, graph. Now I'm going to have to estimate some points, but so be it. So that has a height of 125. For this one, I used a height of 135. So if you're doing this on your own and your answers are slightly different, that's fine. I mean, this is an estimate. So that point, I put about 130. And then my next one here, 110. And then 85. And then I used 65. So that's where I got my y values. I might as well write the 125 here too. Okay, and then I have my trapezoids right along here. I'm not going to, I'll draw them, but they're going to look kind of ugly because I don't have a nice ruler tool for my OneNote. But it is going to be fairly close. There's really not that much distance there. My pen doesn't do it justice. So this is going to be approximately equal to, and I'm just going to pull the 1/2 and the width out, and I'm going to use that trick I did on the front. So I'm going to have 1/100, where we're starting here at 0, plus 2 times 125, plus 2 times 135, plus 2 times 130, plus 2 times 110, plus 2 times 85, plus 65. Okay, and adding that all up, this becomes 2 times 1,335. So this is approximately equal to 2,670 gallons of storm water in 24 hours. I just wrote storm water in the 24-hour period. Okay, so then finally, our old friend we haven't seen for a while, good old marginal cost, which is another way we can work backwards to find accumulation. So find the cost to produce 50 widgets if the initial cost is $1,800 and the marginal cost is equal to this function, 155 minus 30x plus x squared. Let x be the number of items of widgets produced. Let C of x be the cost to produce widgets, and C prime is called, of course, our marginal cost, the cost to produce one additional widget if x items are currently produced. That is, now if you remember this, what you do is your marginal cost is equal to the cost of the next one minus the cost of where you were. So that's the idea we're going to use to do this. So we're going to use the idea that we want to find C of 50. So if we subtract that from that C of 0, that should equal this integral from 0 to 50 of C prime of x dx. And so we're going to substitute in our 0 to 50 of the function they gave us, 155 minus 30x plus x squared dx. And so this becomes 155x minus 15x squared plus 1/3 x cubed, evaluated between 0 and 50. So we get 7750 minus 37,500 plus, and the last number I had to round, 4,166.67, and of course when you substitute 0 in, you get 0. Okay, so our total becomes 11,916.67, and of course we're going to set that equal to C of 50 minus C of 0, and we were given our initial cost was 1,800. So we're going to have 1,800 here equals 11,916.67. So we're going to add that to both sides to get our cost for 50 widgets. So 11,916.67 plus 1,800 is going to equal 13,716.67